Well, good evening. I'm very glad to be here today, traveling around half of the globe to visit Delhi. It's my very first time in India, so it's been really fascinating. I spent the earlier part of the week attending a workshop organized by two real experts here from IUCAA. So Dr. Hsiao-Wen and also Dr. Gupta. So they're going to pretend they don't know what I'm talking about for the next hour or so. So we know, I understand that many of you are students from the physics department, and you are here today on a Saturday evening. You must be very interested in astronomy and astrophysics. So I trust you guys have been keeping up to date about the recent development in ongoing astrophysics research. And over the last few years, we've seen a lot of exciting new discoveries, including many exoplanets in habitable zones, and also the detection of gravitational waves. In one case, we even detect the optical counterpart in the sky. And just last week, we heard about a new record-breaking high redshift quasars. Further bring us back in time within 700 million years after the Big Bang. So these are all very exciting developments. And with more newer and more sensitive, more powerful facilities coming online in the near future, which I understand India is playing a big role in. We can only expect there's more to come, more breakthroughs will come. So today, I'm going to talk about a research area that address fundamental questions concerning the how the large-scale structures we see in the universe today form and evolve. And in particular, I'm going to focus on one important component that we know dominates in maths, but has been largely left out because it's dark. And because it's difficult, it's challenging to capture this dark component. And so I will highlight the kind of progress and future prospect there are in this particular area. So you can see in the beginning slide here, I'm not sure how many of you can recognize this place. What you see in the background, the entire image, you can see the beautiful Chilean night sky. Underneath are the two Magellan telescopes sitting on top of the Atacama Desert in northern Chile. And you can see the Milky Way, this panoramic image that shows you clear dark sky, dark night. This is what we can see without any help of telescopes. So while the Milky Way, this beautiful sky, is as impressive as it is, it actually presents a confusing foreground for those of us who try to study distant objects. So in order to study the cosmos beyond the Milky Way, we actually have to look between stars. So if you just focus over the last decade or so, with a lot of deep, exquisite images have been taken by the Hubble Space Telescope. This is a small area that was taken using the Hubble Space Telescope. It's called the Hubble Ultra Deep Field. You can see that, and this is pointing to supposedly a blank area of the sky, and integrated over a very long exposure time. And what you can see is what seemed to be a blank sky. After you took this long exposure, you see thousands of galaxies. And every one of them looks different from the rest. And actually, I will challenge you to find any two of alike. So they all look different, they have different colors. It looks like not only the visible universe is lumpy, it's blobby, but the galaxies all look very different. it has a diverse range of morphology. So if I just zoom in, so this was actually Hubble. So Hubble discovered these galaxies beyond the Milky Way almost a century ago. And he did his best. He realized everything looks different from the rest. And he did his best to classify, to come up with this Hubble tuning fork diagram. You can see that he kind of grouped the galaxies into round-looking ellipticals to spirals to something with a central barred structure. And so these days we have tons of astronomical images taken. So sometimes we see something that looks like a Mexican hat. Sometimes it looks like a train wreck. And sometimes this is what people call a ring galaxy. So with all the diverse range and seemingly random phenomenon, the surprising thing is it appears that there's actually some simple principles. They actually follow some simple correlations. So to start out, this is so-called galaxy by modality. What shows here is the color in the y-axis and mass in the x-axis. Roughly speaking, what we find is galaxies tend to fall into two different categories. Red tend to be more massive, and blue galaxies. And the red galaxies, they tend to be older, more evolved. And the blue galaxies appear to be younger. Many of them are still forming new stars. So no matter how weird they look, they seem to follow this general trend. And if you look further, there's also a very tight size and mass correlation. Again, I want you to remember back the weird morphologies we saw. So here it shows the so-called half mass radius. Within this radius, within this size here, we see half of the total mass versus the total mass that show at the top axis. Over more than 4 orders of magnitude, we see that more massive galaxies systematically show bigger, are more extended. Again, irrespective of what they look, there seems to be this tight correlation. Just one more. So there's this also so-called metallicity relation. So for those who are new in astronomy, we have a funny way of calling our heavy elements. We call them metal. So the metallicity is a measure of how many heavy elements are there per hydrogen particle. So it's a relative ratio. If there's more heavy element, the metallicity is higher. And it turns out, just like the size-mass correlation, there's also a very tight correlation between mass in the x-axis here and the amount of heavy elements that have been produced over time. So somehow, bigger galaxies are, on average, are older and more massive and also more enriched with heavy elements, irrespective of what they look. So there's this order in chaos that seems to tell us there are some simple underlying driving principles that govern the galaxy formation and evolution. So to astrophysicists, this is good news because there must be ways to be able to reproduce the observed large-scale structure based on some simple principles. And this is a struggle over 2 decades. And it's a success. So just in the last couple years, most of the numerical simulations are able to produce realistic looking galaxies. So here, I have to mention, these are not real. These are simulated galaxies. At the top are the disk spiral types, looked top down, so-called face on. You can see really detailed spiral arms and also dust lands, the dark part, and star forming regions. And when you see the disk spiral edge on, the thin disk is really reproducing the observed central bulge to the disk ratio. Amazing. So like I said, most simulation groups are able to do that now. So this is a separate group that shows that they can reproduce the Hubble tuning fork diagram in their simulation volume. Again, starting from elliptical galaxies evolving to the right to spiral looking, even bar spirals you can see. I also try to capture some train wreck examples. So, declare success, victory. Are we done? Since I'm asking, that means the answer is no. So what is left out? As I said in the beginning, so these days we know very well what the universe is made of. We know about 22% of the entire mass density resides in dark matter, whatever that is. And 74% are in the so-called dark energy. Again, the second fairy tale. So a lot of people are pursuing the nature of the two dark forces. So the tiny little sliver of 4% are what we are made of, regular, ordinary matter. So we know exactly what they are. This is so-called baryon. So in principle, we should know where to find them. Agreed? So when you actually look into the composition, cosmic composition, trying to identify the 4% of the total mass budget in regular matter, we could only identify all the known matter, like stars or gas, together make up just about 10% of all regular matter that we know exists. The rest is still to be found. And considering this is 90% of all the regular matter, this is a serious problem. So now, going back to the success in simulations. So they can reproduce realistic looking galaxies. What about the remaining 90%? So if we look back to, again, one of the numerical simulations, this is showing you the expected spatial distribution of dark matter over about 15 megaparsecs across. So I'm going to use megaparsec. I'm going to use parsec. So this is an astronomical distance measure unit that corresponds to about 3 light years. So again, astronomical number. The universe is so huge, vast space. We have to invent a new unit. And even after we invented 3 light years of parsec, we still need to go up to million parsecs to describe a tiny little volume in the cosmos. So this square here, this panel here, it's about 15 megaparsecs across. And by the way, the solar system, we are about 8,000 parsecs to the galactic center. That gives you a sense of the size of the Milky Way disk. So in the simulations, even though we don't know dark matter, what the dark matter is made of, but it follows very simple physical principle, so we can predict from the first initial density fluctuation what the dark matter distribution is going to be like in the current time. And you can see that it's really rich in structure on all scales. Yes?
What is this image looking at? Is it galactic center?
No, this is just a simulation volume that covers about 15 megaparsecs across. You can imagine, so if the galactic center may be one of these red dots here. For this, to be this big, it's going to be a cluster. So I'm going to, since you asked where's the galactic center. So this is what the simulation predict the spectral distribution for dark matter, how it looks like. So what do you think the galaxies, the distribution for galaxies should look like? Can you find any galaxies here? You need to look hard. Maybe we need to turn the lights off. But you can see that there are tiny small yellow dots in this vast volume. This is what we expect galaxies, how sparsely distributed galaxies are relative to dark matter. So remember, this is 10% of all regular matter. What about the rest of the 90%? So this is what the simulations predict, that the rest of the 90% should exist, should fill up the cosmos along the so-called cosmic web, filamentary structure. So, and the filaments are the crucial fuel that feed the formation of galaxies and continued growth of these galaxies. At least this is what theory expects. So to some extent, we can actually test whether the idea is generally correct. So we can start looking into our own backyard. This is an old sky map of the Milky Way. So again, now it's unwrapped. Remember the all sky image from Chile. It shows the central disk here, and then there's a bulge. That's the galactic center. So this is the optical view. This is what we call optical view of the Milky Way. When we look into 21 centimeter in radial, targeting hydrogen atom, we do see a lot of clouds floating in the Milky Way sky. The only caveat is we don't have a distance. We don't know where they are really, because we are fundamentally kind of blindsided because of the proximity. So if we move beyond the Milky Way to our next door neighbor, Andromeda. So I don't know if you guys can see Andromeda from here. You can? Again, this is the optical image of also called M31. When we look into, again, the radial, we see, again, these clouds floating around the disk. But the difference is this time, because we see from the outside, we know right away that they go all the way out to as far as 50 kiloparsecs. So 50,000 times of a parsec. So what about further away? So this is a galaxy group. That means there's more than one galaxy in this small volume that come from similar proximity. And in the optical image, this is a Sloan Digital Sky Survey image. You can see a giant spiral surrounded by a couple small disk galaxies and this prototype starburst galaxy. Just to zoom in to impress you the kind of detail we know these days. So when we look into radial, what does it look like? The space between galaxies is filled with this hydrogen gas. Again, extend beyond 50 kpc. So qualitatively, at least in terms of the comparison on the surface, it does look like there is extended, there's the tenuous gas around galaxies as expected from theory. So, but how consistent are observations and simulations? Naturally, we want to make a direct comparison over a large volume. But this kind of observation, radio observation, trying to detect this tenuous gas, quickly runs out of steam. You just move slightly beyond the local volume, it became very difficult to detect this kind of gas. So that's why we need to have a new tool, new way of probing this kind of tenuous gas at much larger distance. So what do? So we go back to physics. So this is just to show you, again, a simulation box, the filamentary structure. And that's filled with mostly hydrogen, 99.9% hydrogen. So what do we think could happen when a photon hits one of the hydrogen particles? So physics tells us if the photon is at the right energy, it's going to interact with the electron in hydrogen. And it's going to excite the electron, and the photon gets lost. So if you have a background source, if you have a source that serves as a backlight, shine through this cosmic web, you can imagine that every time the light hits a filament, it's going to create a dip in the backlight. And remember that the universe continues to expand. So the light will be redshifted as things move away from us. So along a finite path, slowly you build up this map of filaments at the right location just by studying where the dip comes in. So this is absorption, absorbing the background light. So just to help you visualize what's happening, this is a very nice movie made by Andrew Ponson at University of College London. As the light from the background source travels through the cosmos to an observer on the right, you'll see that every time, and this is the spectrum, this is the light from the background source. Every time it hits a filament, a dense filament, it's going to create a dip. So let's see if this works. So you can see starting from the source location, every time it hits a dense light, it's going to create a deeper absorption, absorbing a larger fraction of the light. And you see here, this is super dense and then completely absorbed the light below this energy. Yes.
What are the peaks above? Intensity peaks are also there.
See this peak?
Yeah.
This is from the background light. It just is from the, it's like the fingerprint that's associated with the nature, the origin of the object itself. So it has nothing to do with space in between. Just, I want you to focus on the absorption forest. This is what's called lemma alpha forest. By studying the lemma alpha forest, we can construct a one-dimensional map, basically just the map of density fluctuation along one line of sight. So this is what we call core sampling, if you wish. This is equivalent to core sampling of the dark universe using the so-called absorption spectroscopy. So here I just put this cartoon. This again, remember this is the M81 group with the abundant extended gas. Imagine there's a background source shines through the space, and then it's going to produce this so-called lemma alpha forest. And the good thing about absorption spectroscopy is we don't just study hydrogen. So it turns out the lemma alpha forest, a large fraction of them, come with associated features produced by heavy elements. So in the cosmos, in addition to hydrogen, there's also a small fraction of heavy elements So again, if the condition is right, the photon hits the heavy element, it will also be absorbed. And through comparing the relative strength, we can also constrain the chemical enrichment, how much, the fraction of heavy elements that have been produced. So this provides a very sensitive empirical probe of tenuous gas in and around galaxies. So this is a technique that people have been using actually for over 2 decades. The advantage, as I said, is because it's very sensitive. The disadvantage is it's a painstaking process because you can only have one 1D probe. And when it comes to probing gas around galaxies, it's a 3D, it's an extended structure. So we need to have a 2D map. So how do we do it? Essentially, what we end up doing is to identify a large sample of galaxies that happen to sit in front of a background source. So here I just show 6 examples of, every fuzzy yellow blob is a galaxy. And you notice they all have a blue dot next to it at different distances. So this is the background light. By taking, again, the spectrum of the background source, we can identify associated absorption features that are consistent in location with the galaxy. But as they move, you can see the strength of this absorption actually changes as you go further out, further away from the galaxy. And what we can do next is to form sort of the so-called ensemble average. We combine the entire galaxy sample together, forming some sort of a cosmic average, essentially, with quasar, the background source showing up at different locations in the sky. And by examining how the signal changes with the distance to the galaxy, we can build up a cosmic mean, a 1D average of the density profile from the galaxy for the extended gas. So just to visualize, imagine if this galaxy is surrounded by this giant filament that we saw in simulations. Presumably, every background source that hit the filament should produce a strong absorption feature. And by examining the strength, how that changes with distance, that forms as the first order test of the model. And this shows you that we can do this for hydrogen. And this shows you how strong the signal is as a function of distance from the galaxy. Not surprisingly, just like what we see in visible optical disks, how stars are distributed, we see a very fast declining trend as we move further away from the galaxy, indicating that the gas is thinning out as you go away from the central mass. And likewise, we can do that for heavy elements. It also shows very similar trend, but it stops much earlier than hydrogen gas. It indicates that while heavy elements may exist around galaxies, it doesn't extend as far out. So that gives us another hint about how the heavy elements we see away from galaxies are generated. So now with this in mind, we can do this to distance as far away as the background light can be. Unlike in the radio 21 centimeter, we are limited to very nearby universe because of the sensitivity of the instrument. But for this, so long as you can find the background quasar which, as I said, the latest one is within 700 million years after the Big Bang, then you can probe all the way out, the gas all the way out into the early epoch. So now we can compare with a large sample, we can compare with simulations. It turns out there's a problem. So what this showing here is from the simulations that can successfully reproduce realistic looking galaxies. At the top, either it's red or spiral looking galaxies. They underestimate the amount of signal we see out into galactic halos. So while they appear to be able to model the 4%, 10% of the regular matter, they failed in capturing the physics that's driving the rest of the 90%. So what can we do to help improve our understanding of this subject? So if we go back, so this brings us to the ongoing research project and the future development. So we come back to this image, looking at this extended gas around M81 again. If you look carefully, just by morphology again, an image can tell many different things. If you look at the image, you see different structures. From something as simple as a rotating disk in the middle to, there's the gas being stripped out of a galaxy here, one of the group members, to something that looks like tidal tail. Due to tidal force, material gets stripped out of the galaxy, to some sort of free-floating clouds. And they all have different motion. Like rotating disk, by design, it should be just spinning. But stripped gas has very distinct directional motion. And these clouds, they will just be randomly floating around the galaxy. So not only the spatial distribution is distinct between these different components, their motion is also different, from organized, coherent spinning to something that's more random. So that gives us a hint. To really bridge the gap between observations and simulations, we really need to have a map. 1D probe just doesn't seem to be enough. It brought us closer. It gave us new insight, but now we need more. So what can we do? So down here you can see the hint of filaments coming in, just to tie back with the simulation result. One more component, that's the starburst-driven outflow. So this is really energetic wings that's being brought out by intense star formation in the galaxy, contradictory to the kind of spinning disk structure. The distinct morphology is this conical outflows. Again, the directional, very orthogonal, completely independent of what we see here. Just to highlight the prospect of sorting through these complex physical processes if we have a spatially resolved map of the gas. So essentially, we want to go back to making radio more powerful, but we don't have to. So one of the new approaches is to utilize multiply lensed background source due to the foreground mass concentration. This is the so-called gravitational lensing, going back to Einstein's general relativity, space-time gets distorted when there's a huge amount of mass present. And through gravitational lensing, single background source gets split into multiples. So by observing the multiply lensed images, we immediately expand the number of probes from 1 to 4 in this case. So that's a factor of 4 gain. That's pretty good. So just to give you an idea about what might be possible with the multiple probes, in a very simplified world, imagine if there's a spinning spiral galaxy. In this case, we are seeing the galaxy from top down. But if there's an observer that's viewing the galaxy from sideways, so we put the observer down here, looking up through the disk. And remember the disk is spinning. So I'm gonna resort to Doppler shift again. Different motion will move the features different according to how fast the disk is moving. And also I should add that one thing you can see is the light is brighter, much brighter at the center and gradually decline to the outskirt. So you can infer that the density is dropping as you go to the outskirt. So coupled with the motion, what do we expect to see in the spectral feature due to the spinning disk? So if I just highlight 2 points, one closer to the center of the galaxy, and almost the motion of the disk almost goes in parallel with the line of sight. That means just by observing the velocity offset, we capture most of the rotation motion. The projection is nearly 100%. In contrast to this point, a point in the outskirt further away, the density is lower, and it's moving almost perpendicular to the line of sight. That means the projection will be near 0. I hope that's clear. So on the left, you can see that near the center, almost parallel to the line of sight, there's a strong signal, and most redshifted. It's moving away from the observer. The strongest component is also most redshifted. As you go further away, the density declines, absorption strength declines, and you see that the weakest component appears as something that's closer to the systemic velocity of the galaxy. So if you understand this, now I'm going to put in a second side line, opposite side from of the center. So now, how does the disk move? So also the observer stands at the same place. The disk here is moving toward the observer on this side of the disk, right? So what we see is closer to the center, the strongest component is going to be most blue shifted. And the weakest component will be closer to 0 relative velocity. So do you see the difference? Opposite side, mirror image. So this is, you can call this a definitive identification of a rotation disk if you have more than one side line. A second example would be the starburst outflows that I said before. There's this biconical feature. So again, in the idealized experiment, if we put an observer on the left, looking at the disk face on in this case now. And again, two sidelines on the opposite side of the disk. Instead of seeing this kind of mirror image, asymmetric profile, we see something that's more or less symmetric. One blue shifted, one red shifted on both sides. So if we see these features, we can identify the process, the physical process that's driving the absorption, the absorbing gas that produces this feature here. And now with a lot of all-sky surveys, so we started with Sloan Digital Sky Survey, and now we are actively building the large synoptic telescope in Chile that's gonna do an all southern sky survey to very deep level. It's gonna, the survey combined is gonna produce thousands of those gravitationally lensed objects that will help with this kind of study. So the future is really bright. But we can actually do better than that. So I talked about absorption. So absorption is when a photon comes in, interact with the electron, and then boosts the electron to higher state, the photon gets lost. But the electron is not gonna stay up there forever. There's the reverse process. In very short time, especially for hydrogen, the electron is gonna come down. It's gonna lose energy, and it will emit a photon. So this is very obvious. So why did we not do this in the first place? The challenge here is when the when the electron comes down, the photon is emitted in any random direction. So every absorption, the signal, when it gets emitted, is diluted by the entire solid angle, the entire sky. So you can imagine the signal is significantly weaker. But in principle, you can do it. And it's actually just being feasible now, given the advancement in instrumentation, in astronomical instrumentation, and also detector technology. And here is an example of the recent detection of this large-scale, low luminosity emission around very distant object. So to facilitate this kind of study, this was made possible by this idea of image slicer. So what is an image slicer? Literally, we slice, given a 2D, two-dimensional image, essentially we put a slit along the entire frame. We cut it up into a thin slit and realign them into a pseudo long slit and send that to a disperser, a prism, to disperse the light. And after the light is dispersed, we repackage the pseudo slit back to its original form. It's like playing the Lego blocks. But in this case, we have an image for every photon energy. So it's trying to highlight here, for blue photons, we can build an image. For green photons, we can build another image, and we can look at how different things are. Why do we want to do that? Because the emission I said earlier, while it's being diluted by the entire sky, it's only coming from very narrow very narrow energy range. The wavelength is narrow. Doing this image slicer allows us to identify the slice we want that targets that energy range we want, that exact photon we want. And I'm going to show you this very nice example that was just obtained recently. it's so what you see here is actually an HST image of the field around a luminous quasar, this supermassive black hole, being powered by supermassive black hole at redshift 0.6. So I use another word, redshift. So in essentially, this is about 4 or 5 billion years from now, 4 or 5 billion years ago. And that's the quasar in the middle. It looks just like a star. And surrounding the quasar, you see many galaxies. I hope you can see in the back that there's spiral-looking galaxy. There are things that look like interacting, like in the stage of making a train wreck. And then there's nothing. The rest is just dark space. So recently, there's a new set of data obtained using the image slicer technology. And that allows us to extract the spectrum of every single pixel in this image. So what I did here is I just collect all the pixels that coincide with the quasar here and build the quasar spectrum down here. These are all typical emission line features that you asked earlier that's associated with the central engine. But because we know what they are, we use these features to identify the exact location of the quasar. And because this is pretty much noiseless, we can determine the location very precisely, very accurately. So now I can, again, going back to the image slicing idea, now using the same data set, I can focus on one specific wavelength and look at the field, what it looks like. And I hope you can see a very good one-to-one comparison. The only difference here is this is a space telescope image. It looks much sharper without the atmosphere. This is obtained from the ground. So the atmosphere, you go out to see stars, they twinkle. So this atmosphere really smeared the image quite a bit. But aside from that, you can see there's pretty much a very good one-to-one comparison. There's all the galaxies you find in the Hubble Space Telescope image and in the ground-based image here. And if I move to a narrower line region, again, we can look at the image side by side. They still look pretty similar except for this part. I hope you can see this does not have a counterpart in the space image. So something different is happening. What is this? So what I'm going to do next is to show you a movie of this field stepping through the wavelength centered around this narrow line. The entire field, though. So the narrow line is set by the location of the quasar. But I'm going to show you what the image, the field, looks like as we step through different wavelengths. And I can convert that to relative velocity. In doing so, I will remove, let's see, this is not going to come. I already removed the quasar light in this frame, just so you can see the surrounding much better. So I'm going to start the movie at about 1400 kilometers per second, blue shifted in front, well, moving toward us from the quasar position. Does that make sense? From negative 1400 kilometers per second to plus, moving toward, further away to plus 300 kilometers per second. What you're going to see, I'm just going to tell you what you're going to see, is at this location, that bright string, the knot, doesn't exist, right? Disappeared. So starting from about 1370 kilometers per second, you will see gas, signal being extended out of this interacting pair here. You're going to see signal from here and the train wreck, a mess, and the signal is going to move to this side, the left side, where you see 1, 2, 3, 4, 5, 6, 7 galaxies there. It turns out that they are all interacting like crazy. They are all pulling each other like crazy. And then you're going to see the signal move to that streak you saw earlier and pointing directly to where the quasar is. So I'm going to start the movie now. So you see, starting from here, there's gas being pulled out of the interacting galaxy. Then it moves here at about minus 500 kilometers per second. These similarly isolated galaxies are interacting like crazy. And then there's the streak feeding into the center of the quasar. Should I do this again? Maybe I'll do this again. So starting, again, gas being tightly stripped out of the galaxy, and then here you can see the streak. And then it's going to come in here. There may have been a dwarf being destroyed some time ago, and then gas started to show up right at where the quasar is. So this is what I would say, the so-called co-evolution between supermassive black hole feeding and halo gas caught in action for the first time. So again, just to summarize, this is a snapshot of that HSD image to highlight where the galaxies are. And this is different panel of the gas in different wavelength slice, velocity slice. So just to compare with what we saw earlier in radio. So remember, the idea is to have spatially resolved data using both the morphology and velocity field to identify the process that's driving that's dictating the content of the halo gas. So we are very close. And like I said, this instrument was only commissioned a couple years ago. There's a lot more to come. So now I'm toward the end. This is the end of my talk. So I just close. I hope you're convinced that we are really, in terms of astrophysics research, this is really an exciting time for us. A lot has happened, but a lot more are going to happen. And for those who are interested in pursuing this, I want to end with this quote from Dr. Vera Rubin, who sadly passed away last year. Does anybody know who she is? Yes?
She found out the rotational curves in the galaxies.
Yes. She found the first, she discovered the first empirical piece of evidence for dark matter through observation of the rotation velocity is flattened. So she had a lot of wise words, but this one stuck with me. So naturally, given what she did, what she accomplished, don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the real mystery lies. I will just end here.